So far we have studied that when say the circuit is supplied by a DC source, it is giving to the steady state pattern. In this particular lecture, we are going to analyze the transient behavior in the DC circuits. So that transients are arising because of the operation of the switch. So because of this switch, the operating conditions are changing and that particular is giving rise to the transients. The constitutive relationship for the resistance suggests V is equal to IR. It is known to us. However, the important point is that it is having no dependency on time. For the capacitance, we know that IC is equal to C dVc upon dt. So that particular d upon dt term suggests it is having a time dependency. However, we know that the voltage across the capacitor cannot change instantaneously. That suggests that the voltage must be continuous across the capacitor. However, there is no restriction on the current. This continuity of the voltage suggests Vc is 0 minus is equal to Vc 0 plus. So that 0 minus and 0 plus are the situations immediately before and after the switch operations. When say the DC is supplied continuously, the capacitor gets fully charged and it behaves as an open circuit. For the inductance, we know that V is equal to L di upon dt. So there is a term d upon dt which suggests that it is having a time dependency. We have already gone through that the current through the inductor cannot change instantaneously, or you can say the current must be continuous. This continuity is explained by the relation IL 0 minus is equal to IL 0 plus. So this 0 minus 0 plus are with respect to the switch operations, likewise as explained previously. So for the DC, the inductor behaves as short circuit. So the transient situation arises when the circuit is consisting of a energy storage elements, that is either inductor or capacitor, or say the combination both. So this particular further arises because there is there is a switch operation. Now the important point here is that instead of the algebraic equations, it is giving rise to the differential equations of KCL and KVL. Now because of this particular time dependency term, the circuit is becoming dynamic, or this dynamic word itself carries the meaning of that it is having a time dependency. This particular includes both the transient and the steady state components in the response. So as mentioned that the transient response, it is depending on the time, it is of temporary nature and it continues to decay and vanishes with the time for a stable system. The steady state response, it is not depending on the time. So normally we used to carry out the dy upon dt and making it equal to 0, that is suggesting that it has attained the steady state value. However, for the AC system, if it is coming out to be of periodic nature, that particular is also regarded as the steady state response. We will not be considering this periodic nature behavior in this, because we have to go for the input from the DC supply. Complete response is defined as the sum of transient or natural response plus the steady state and the forced response likewise. In mathematics term, the transient response is regarded as the homogeneous solution, where say the steady state or forced response is defined as a particular solution. Now we have to carry out the analysis for the first order and the second order systems. So the first order suggests that the highest order of the differential equation is of first order, where in the second order the highest order of differential equation is of second order. So the first order situation arises when say it is having one type of energy storage elements, let's say the circuit is consisting of capacitors only, or say the circuit is consisting of inductors only in addition to the resistance. In the second order, both type of energy storage elements are to be present, which are giving rise to the combination of RLC, or you can say pure LC circuit. As mentioned that we are going to analyze for the first order system, so RC or RL circuits are considered. Now in this particular, we will be analyzing the source free response. So that source free means the response is initiated because of only the initial conditions. Now this particular is a RC circuit which we are considering. On this particular circuit you will not be seeing any external source, so that is coming out to be a source free nature. However, this capacitor got initially charged because of the some arrangement, or you can say before the switch operation, to the initial voltage level of V0. Because of this initially charged voltage, initial voltage level, it has attained the energy half CV square. Now in this particular diagram, and say the capacitor is charged likewise, so we are saying it is charged to the upper plate as positive, lower plate as negative. This is divided into, represented by say the two node problem. So this is taken as a ground, other node voltage is expressed as V, and we are able to write the KCL at this IC plus IR is equal to 0. This relationship, VI relationship is substituted here, so it is giving rise to the dV by dt is equal to minus V upon RC. This equation is rearranged into the form so that the voltage terms are coming out to be on one side, the time constant and the coefficient terms are on the other side likewise. And when say the integration is attempted, we will be getting the equation log of V is equal to minus T upon RC plus log of A. This A is the proportionality constant to be identified by the initial conditions. So this equation is rearranged into the form, it is giving rise to the Vt is equal to A e to the power minus T upon RC. When say we are interested in calculating this coefficient A, we have substituted the initial conditions, that is giving rise to the value A is equal to V0. So that particular is there. Now RC, which is the time represented as a time constant, likewise. So the standard solution of this source free capacitor voltage is expressed by Vt is equal to V0 e to the power minus T upon tau. Now the point which are to be important, that this particular response is initiated because of the initial voltage or initial energy. It is not due to the external source that has been highlighted previously. This is regarded as a natural response as mentioned previously, and it represents the physical characteristic. So the physical characteristics means this particular rate of decrease etc. is decided by the time constant, which are governed purely by the resistance and capacitance, which are the physical characteristics, or you can say the system parameters. Now to further elaborate, if suppose say we keep on increasing the time, and when say the time t is becoming equal to the tau, equal to the time constant, it is attaining the level 0.368 of the V0, or you can say 36.8 of the initial 38.6% of the initial voltage level. So on that basis, you can say define the time constant is the time required for the response to decay to 36.8% of its initial value. Here say the important point is 36.8% of its initial value. Otherwise, in general sense, the time constant is defined as the rapidity with which the voltage decreases. Now this time constant can further be explained by the other interpretation. If we are calculating the slope at a initial point, or you can say the initial slope is calculated likewise. So initial slope suggests you are calculating the dV upon dt at time t is equal to 0. This particular is a normalized one, so we are calculating the derivative of V upon V0. This particular is giving rise to the minus 1 upon tau. So this initial slope is indicated likewise extended, and if suppose say the voltage level continues to decrease by this initial rate of decrease, it will be attaining the 0 value, which is the steady state value in the time t is equal to tau. Now this particular tau is having a significant influence on the behavior, or you can say the rate of decrease. So when say the time constant is high, the rate of decrease is low. When say the time constant is small, the rate of decrease is high. And On this particular basis, when we are seeing that when say the time is coming out to be 5 times the time constant, it is coming out to be close to the steady state value. Numerically, the value at 5 times the time constant is coming out to be within 1%, that is precisely 0.00674 of the initial voltage. So that particular can be regarded as the steady state value, or we can say the system has attained the steady state value when say the time is expanded by 5 times the time constant. So in the case of RC circuit, first point is to calculate the voltage. After calculating the voltage, we can calculate, or we are free to calculate the current through the resistor, current through the capacitor. Likewise, they are coming out to be of negative nature. So IC is negative to the IR. This particular holds true the KCL relation that we have worked out, but physically it suggests that the actual current direction is opposite to what has been taken as a reference. So we have taken the current direction as downward. However, when say the capacitor gets charged with the upper plate positive, the current direction will be outward through the upper terminal. The power dissipated is instantaneous power. So that particular is instantaneous voltage multiplied by the current through the resistor. So energy absorbed during the time 0 to t, it is obtained likewise. So this particular is giving an interesting understanding, which is a continuous function of time. However, when say the time t is approaching to infinity, this value comes out to be exactly equal to whatever say the initially stored energy in the capacitor. So in that period, whole of the energy stored in the capacitor is getting dissipated as heat in the resistor. Now after going through the RC circuit behavior, we are now in a position to analyze the RL circuit behavior. Only point which is to be understood that the current direction is unchanged. So initially the current direction was such that the current was coming out to be entering to this bottom terminal through the inductor, because this particular terminal is marked positive. So the current direction is kept unchanged. As say the current is common, so we will be writing the KVL equation. That particular is suggesting the KVL LdI upon dt plus IR is equal to 0. That has been worked out. We have rearranged the equation, so the current terms are coming out to be on one side. Other term is having the time dependent term. This is solved by the same arrangement. We will be having say the general solution like I is equal to a e to the power minus r upon L into t. This A coefficient is calculated by the initial condition, so that current through the inductor initially was I0. So that particular is giving to the characteristic like IT is equal to I0 e to the power minus t upon tau, where say we will be defining the tau as L upon R. So this particular is also due to the initial inductor current. As mentioned previously, this characteristic is referred as the natural response characteristics, and it is due to the physical characteristic of physical or numerical value of the inductor and capacitors. So this particular can also be explained with the initial rate of decrease of the current that has been on the analogous line for the RC circuit, and the time constant is also influencing this characteristic. So when say the time constant is large, the rate of decrease will be low, or when say the time constant is low, the rate of decrease will be high. So in case of RL circuit, we are first driving the relationship for the current. Thereafter we are driving the relationship for the voltage across the resistor, voltage across the inductor. Now voltage across the resistor and voltage across the inductor, when added, they are coming out to be 0. That particular is coming out to be true with these numerical values. However, this negative value of the inductor voltage is suggesting something, that the current is decreasing. So current, although is in the same direction, but it is decreasing. So because of this, the inductor voltage is coming out to be of negative polarity. On the similar line, we can calculate the power dissipated, energy absorbed expression. When say the time t is tending towards infinity, the whole of the energy stored in the inductor will be dissipated as a heat in the resistance. Now the steps to solve it has, so the steps which are involved in this, it is, we have to first represent the circuit before the switch operation and assume that it has attained the steady state. Thereafter we will be able to calculate the I0 in case of the inductor RL circuit, or V0 in case of the RC circuit. Thereafter we have to find out the equivalent after the switch operation. In the equivalent, we considered only one energy storage element, so the resistance can be many or combinations likewise. So we will be calculating the equivalent of the resistance. On that equivalent basis, we will be calculating the time coefficients for the RC or RL circuits. Thereafter, the behavior can be calculated. So now let us take some examples where say this particular operation before the switching and after the switching is explained and how we can solve it. So in this we have to calculate the voltage, the current through the capacitor likewise, and this particular direction is indicated that the switch is opened at time t is equal to 0. So previous to this operation the switch was closed. As we have mentioned that this particular is coming out to be the circuit behavior. So this is a fully closed operation. This capacitor is getting charged fully and it will be behaving as open circuit. So whatever say the voltage across this capacitor will be decided by the resistances and so on. So how we will be approaching? These two resistances are in parallel, so that particular is resulting into the 3 ohm value. 6 and the 3 ohm, they are forming the series arrangement. So the current is calculated likewise, 24 upon 9. This particular is to be multiplied by this 3, so it is giving rise to the 8 volt. On the similar initial energy half CV square, so that particular is calculated 5.66 joule. Now when say the switching is affected, so the intention here is that it is open, so this particular supply voltage is removed, 6 ohm resistance is also removed, the circuit will look like this. However, this capacitor is initially charged to the level V0 and this is going to decide the behavior of the circuit. So the intention is to find out the equivalent. In this, the equivalent is the parallel combination of these two resistance, which is likewise. Once the equivalent R and the capacitor is known, we can calculate the time coefficient, time constant. Thereafter, we will be able to calculate the behavior. So this is the initial voltage 8, time coefficient 0.5, so the relationship likewise, and finally we can calculate the capacitor current. Take the other example for the RL circuit. In this particular, the intention is to calculate the inductor current when say the switch is opened at time t is equal to 0. So previously the switch was closed for sufficient long time. As a starting point, when say the switch was closed for sufficient long time, the inductor is behaving like a short circuit. So because of this short circuit, there is also a shorted path here, there is no current in this 5 ohm resistor. So it is behaving like the whole of the supply current is getting divided into the two parallel branch. So because of this, the initial inductor current I0 is calculated as 2 ampere. That particular is giving rise to the inductor energy to the level of 4 joule. When says the switch is operated, so the circuit will be looking like this. There is no external supply. It is a free response arrangement. Because of this, this 12 ohm and 8 ohm are coming out to be in series. So they are resulting into the 20 ohm. That 20 ohm will be in parallel with the 5 ohm. So that is giving rise to the equivalent resistance as 4 ohm. Because of this equivalent resistance and the inductance value, we calculated the time constant as 0.5 seconds. So in this, the free response current of the inductor is expressed by I0 e to the power minus t upon tau, which is 2 e to the power minus 2t. Correspondingly, we can calculate the voltage, which has been calculated as minus 8 e to the power minus 2t, and the other parameters of interest. Now it's time to put a summary. We can summarize it that the transient conditions arises when, say, there is a switch operation. That switch operation can be opening or closing of the switch. The free response characteristics is defined by I0 e to the power minus t upon tau for the inductor current in the RL circuit and V0 e to the power minus t upon tau for the capacitor voltage in the RC circuit. As a reminder, you are requested to first obtain the capacitor voltage Vc or the inductor current RL in, in the RL circuit. Thereafter, calculate the other parameters of interest. Lastly, the time constant is defined as the time expended to decrease the voltage in the RC or the current in the RL to 36.8% of its initial value. So thanks. We will be considering the step response in the next. For further reading, you can have a book likewise.